whole atmosphere model and chemistry working group joint seminars. This morning we're going to be hearing from Alyssa Stansfield of Colorado State University. So she's currently an NSF AGS postdoctoral fellow working under Kristen Rasmussen. She obtained her BS in meteorology and marine science from Rutgers University, and then a PhD in atmospheric sciences from Stony Brook, working under Dr. Kevin Reed. And for her doctoral thesis, she worked on tropical cyclones under future climate conditions and actually is going to be speaking with us today on that very topic. So just a quick reminder, questions at the end of the seminar, please. And for those that are online watching through YouTube, you will be able to ask questions. To do so, please go to slido.com and look for the CGD seminar page. No S, just CGD seminar. And we'll be able to take your questions at the end along with questions that are coming from the in-person audience. Okay, thank you.
Thank you. So thanks everyone for coming. Thank you for inviting me. I just wanted to say that I first came to NCAR as part of the undergraduate leadership workshop in 2016, and I still remember getting to talk to the scientists here, and so it's really cool to come here and give a seminar now. So this I'll be presenting today is kind of mostly my PhD dissertation research, and then getting into now what I'm doing at CSU for my postdoc. So I just want to thank Kristen, my advisor Kevin Reed, and then all my other collaborators who kind of helped me through my PhD. And so thankfully my work is really easy to motivate. We all know every year tropical cyclones come through all over the world, cause a lot of economic damage and unfortunately injuries and death. And so most fatalities at least, and I think also economic damage is water related, so mostly flooding. And so many aspects or many different factors go into causing tropical cyclone flooding, but what I mostly focus on is the precipitation aspect. And so looking into how tropical cyclone precipitation will change in the future, I mean, there's been kind of many studies on this, kind of just using historical climate model simulations and then kind of comparing them to future climate model simulations under different RCP or SSP scenarios. And so this kind of summary paper came out in 2020, Knudsen et al. And so they kind of tried to summarize all these papers looking at future changes in tropical cyclones. And so what they found was kind of a median increase of about 14% for 2 degrees Celsius of warming. So this is pretty close to the Clausius-Clapeyron rate of about 7% per degree Celsius. But kind of the exact results depend on the model and the precipitation metric, what years you're looking at, et cetera. So you can kind of see that global, those error bars are just the spread of the different expectations. And so, looking at projecting changes in TC precipitation, typically, again, we use climate models. As grid spacing decreases, TCs generally are simulated more accurately with more realistic intensities and internal structures. But unfortunately, when you're trying to run high-resolution climate models for decades to hundreds of years, I'm sure everyone knows it's expensive computationally. So one method to reduce this cost is to use variable resolution models. And if you're looking at a TC basin specifically, like here, I'm going to look at the North Atlantic Basin. Variable resolution is kind of nice because you can just kind of focus on your region of interest. And so this first part, I'm going to go through quickly, but how will TC precipitation over the eastern US change in the future? So I use these 3 variable resolution CAM5 simulations. They each have 3 ensemble members. So the first is a historical kind of AMIP type simulation for 1985 to 2014. It'll be referred to as REF in the figures, and then an RCP 4.5 and RCP 8.5 for the end of century. And so looking at TC track density, so in the future, the average TC track density decreases over a lot of the East Coast, especially the Gulf and Florida and Southeast. When you look at the extreme precipitation that's coming from these storms, so this is just one metric, annual maximum 5-day cumulative precipitation, you see that when you're comparing the ref, so the top row, to the two RCP simulations, there actually are decreases in the annual mean extreme precipitation coming from tropical cyclones over kind of most of the coast, not always. And then when you take this middle column and you divide it by the column all the way on the left, you get this metric that we call scaled RX5 day. And so basically it's just showing you the rainfall that you get per hour of TC impact at that location. And so you see that, especially along the Gulf Coast in the two RCP simulations, you're seeing kind of more rainfall per every hour of TC impact. And so just to summarize quickly, this first part, early in my PhD kind of looked at these future simulations, compared them to a historical simulation. At least in Cam 5, it seems that less TCs make landfall in the eastern US in the future. On average, the TCs are more intense and larger. I didn't show that in this presentation. In many areas, the annual mean overland TC precipitation actually decreases. But when you look at the precipitation per hour of impact, it actually increases. So I think this is important on like a human impacts perspective. When you get more extreme precipitation, maybe in the same or less amount of time, this could definitely worsen flooding in the future. And then I think it also can make like single TC events more impactful, even in seasons that are kind of not as active. So for example, the 2022 season, there weren't many storms, they weren't making landfall, and then Hurricane Fiona and Hurricane Ian kind of both came in, and I think sometimes it makes people complacent when they're seeing a not as active season, and then a storm can come in and really do a lot of damage. So this was kind of early in my PhD, so then I was thinking about what I want to do for the rest of my time at Stony Brook. And so what I really thought of is, can we take these results and kind of generalize them to predict how much more TC precipitation we expect with each degree Celsius of warming, kind of look at TCs more globally and without kind of relying on these specific future emission scenarios, since we are uncertain what future we're going to follow. And then the other question I wanted to look at was how much of these precipitation increases are coming from just an increase in atmospheric moisture versus changes in TC characteristics like increasing intensity. And so when you're talking about this kind of breakdown of changes in thermodynamics versus dynamics, looking at extreme precipitation, so this is an uncertainty in just general extreme precipitation research. So this figure is from the most recent IPCZ Working Group 1 report. And so the left is showing the total expected change in some metric of extreme precipitation, the annual maximum. The middle is showing what they estimate as the thermodynamic contribution, which is pretty certain and kind of even over most of the globe. And then all the way on the right is the dynamic contribution, which where those hatched areas is where there's low model agreement. So we see that most of this uncertainty does come from the dynamic contribution. And so we'll see it's kind of the same, I think, for tropical cyclones as well. And so to look at these questions that I just kind of mentioned before, I wanted to kind of try to use idealized models to isolate the impacts of thermodynamics versus dynamics in kind of the most simple way I could think of. And so as I mentioned in the beginning, there's a lot of factors that impact TC precipitation. The intensity, obviously, the precipitation rates in the storm. If you're looking at a specific location like the eastern US, it's the number of landfalls, it's their translation speed, and interactions with extratropical systems. So there's a lot that goes into it. And so what I kind of tried to do with these idealized simulations was take out these other factors that are in the gray, so not looking at any landfalls, see if there's any changes in translation speeds. There really aren't in these simulations. And less interactions with other systems, and kind of just isolate these thermodynamic and dynamic factors on the right. And so I used, again, the Community Atmosphere Model version 5, using the protocols of the Radiative Convective Equilibrium Model Intercomparison Project. Such a handful every time I say it, except I added rotation. So the RC-EMIP simulations don't usually have rotation. And so this is using CESM2 with the QP RC-EMIP comp set, which is detailed in a paper by my advisor from 2021. And so I ran 11 simulations with globally uniform sea surface temperature that varies from 295 to 305 Kelvin in 1 Kelvin increments. So again, there's 11 different simulations with different uniform SSTs. I ran each simulation for 2 years. These are RC simulations, so there's no seasonal or diurnal cycles. I'll show you in a minute what these simulations kind of look like. The horizontal grid spacing is like it's about 28 kilometers. I think it's the NE120 grid using the SC dynamical core. And so why use these RC simulations? Again, because there's no land in these, there's no SST variability, there's a very reduced general circulation, and so kind of solely focusing on the TCs themselves and not their interactions with these complex environments. And additionally, again, this is way less computationally expensive than the realistic decades-long model simulations, but it produces a lot more TCs in that same amount of time, or 2 years. You know, I get many more TCs that actually happen in the real world. So you can just look at, do more robust statistics, I guess. And so what do these simulations look like? So this is an animation of wind speed on the 300 Kelvin simulation. And so all of these little dots you see moving around are tropical cyclones. So if you kind of watch it for a while, they form in the tropics and subtropics, and then move kind of west and northward due to beta drift. And then they kind of glob up near the poles and like spin around each other, die off, and kind of interact, which is pretty interesting. And I'll just note that TCs are tracked using the Tempest Extreme software package. And so looking at the characteristics of these TCs, looking at one metric, so their lifetime maximum intensity tends to increase with SST. So as you go from those cooler to warmer colors on the plot, the SST is increasing. The diamonds on the bottom show the median lifetime maximum intensity. And so we see increases in not only the median, but also the maximum lifetime maximum intensity, which is kind of consistent with Kerry Emanuel's potential intensity theory, whoever's familiar with that. And one other note that I thought was interesting was that we saw increased instances of rapid intensification in these simulations as the SST increased. So that's just when the TC intensity increases a lot in kind of a short amount of time. There's been some work showing that this instances of rapid intensification have been increasing in observations. So I just thought it was kind of interesting that we saw the same thing happening in these super idealized simulations as the SST increases. I didn't really look too much more into it, but I just thought it was interesting to note. And so these are showing composites of the TC precipitation in these different simulations. So if you look in the top left of each panel, that shows the SST of the simulation, and then N on the bottom is just the number of samples that go into the composites. And so I'll note that the precipitation analysis that I'm going to show is only for TCs between 40 degrees south and 40 degrees north, because I didn't want to have any impacts from all the SSTs interacting near the poles and running into each other and whatever. So I kind of just limit it to 40 to 40, but still had plenty of samples to look at. And so what's immediately you can notice is the maximum, in extreme precipitation rates, especially within the inner cores of these storms, increase a lot as SST increases. And then also it seems that the kind of size of the precipitation field increases as well. And so next what I tried to do was kind of break this increase in TC precipitation into, again, a thermodynamic component and a dynamic component, where the thermodynamics is basically just an increase in the moisture available, which we would expect to increase at about 7% per Kelvin or degree Celsius. And then the dynamics, I tried to break down into a change in TC intensity, which models and potential intensity theory predict we should have an increase in TC intensity in the future. And then changes in TC size, so like outer size of the storm, measured by the radius of the 8 meter per second wind. And so the models for the future or theory is a little more dicey on this subject. Models kind of predict either no change in TC size or maybe like a slight increase depending on basin. And so I won't talk about this too much, but I kind of just used this equation where partial derivatives kind of broke down the change in precip based on sea surface temperature, V, which is intensity, and R, which is the outer size. And I used a combination of just linear regressions of changes in intensity and outer size, and like a Poisson regression of the precipitation increase to kind of break this down. And again, this is with the goal of breaking down into thermodynamics versus dynamics and kind of not taking into account or kind of ignoring any small changes in these other factors if there are any. And so what we found looking at the 99th percentile of precipitation within each of these storms, the total change in TC precipitation was about 8.6% per Kelvin, with about 67% or so coming from the thermodynamic contribution, about 20% from the intensity contribution, and then about 3%, not too much, I think even less than 3% coming from the outer size. And so summarizing these results, so in these idealized CAM5 RCE simulations, when you have warmer SSTs, that leads to less TCs at any one time, so I didn't show that result. On average, the TCs are more intense and slightly larger as the SST increases, and you see more extreme precipitation rates. When I investigated, the TC precipitation increase a little further, I found that, one, the results do depend a little bit on precipitation metrics, so I did look at other precipitation metrics besides 99th. The results are generally consistent, but there is some variability. And then the increase seems to be around a little bit above the Clausius-Clapeyron rate, with the, dominated by the thermodynamic contribution, so the atmospheric moisture increase with SST. And then the outer size changes contributed little to the extreme precipitation increase. So we did see slight increase in outer size, but I think it's not too surprising that like an outer size increase, I don't think doesn't contribute too much to the extreme precipitation seen in like the core of the storm. And so I think when I was presenting this before, I thought I should add some of the caveats of these idealized simulations. I think it's kind of important to acknowledge the downsides of these, but I still think they are useful. And so again, these simulations do lack real-world features that do impact CC precipitation, intensity, and size. So for example, there isn't really very strong vertical wind shear in these simulations. There's no like extratropical fronts. There's no land, obviously it's an aquaplanet. No SST gradients, diurnal cycle. So these factors, likely do impact the thermodynamic versus dynamic breakdown, but, my idea was kind of to get at the core of this idea and see how simple I could get it. And then again, these are atmosphere-only simulations. There's no ocean coupling, so there's a lack of like feedbacks between TCs and the ocean. This is known to have, feedbacks are known to have an impact on intensity, so this likely would impact precipitation as well. And then again, grid spacing of about 28 kilometers is definitely not fine enough to really simulate the strongest tropical cyclones that we see in observations and like the small scale processes within TCs. So that's another caveat as well. But I think I'll talk a little bit more about that at the end and with my current work. But these results from the idealized simulations are kind of consistent with other studies that have been coming out using very different methods and observations. So again, most climate models, even fully coupled long-term simulations, predict either a decrease or no change in global TC frequency and an increase in average intensity with climate change. So again, those are consistent. This recent study, Kim et al., used this parametric rainfall model, thought was interesting. And they found, again, that changes in accumulated rainfall from TCs is associated with both an increase in intensity and total column water vapor, but the changes can mostly be accounted for by those increases in total column water vapor only. So they also found that it was mostly like a thermodynamic effect and the intensity was secondary. And then this other study from 2022, Shearer et al., used this kind of high resolution observational TC or rainfall product and looked at increases in TC precipitation globally from 1980 to 2019. And they found about 11% per Kelvin increase over that time. So, not exactly what I'm finding, but in the ballpark. So next, and this part is what I'm kind of still working on now. This is kind of last part of my dissertation, is can we take these idealized simulations and can we use them to understand changes in TC precipitation in more realistic simulations and then also ideally observations. And so when I started doing this work, I realized that looking at these changes with SST is not as straightforward, I think, as I originally thought, because there's kind of two different time scales you can look at when you're looking at the relationship of extreme precipitation and temperature. And so there's what's called kind of in the extreme precipitation literature as apparent scaling. And so this is just like the present day variability, kind of like weather time scale of a hurricane is moving over an SST and like what's its precipitation at that time. But then there's also what's called the climate scaling, which is that SSTs are increasing over time. And is TC precipitation responding to that increase on like the long term? And these are not necessarily the same thing. I think they could be equal in the same, but I think there is some kind of distinguishing factor, or you kind of have to think about these differences. And so this is talked again a lot about in like the general extreme precipitation literature. And so people have found just looking at global 99th percentile precipitation or over certain areas that the extreme precipitation temperature relationship can depend on storm type, what season you're looking at, and then also like very localized convective feedbacks. And so people have found localized like sub-daily increases like way above the Clausius-Clapeyron baseline, even in observations at like certain locations. A lot of the studies I found have kind of looked at places in Europe. And so again, it's kind of uncertain how the present day variability, so this apparent scaling, relates to this climate change response or the climate scaling. And so people have been looking at this in the extreme precipitation literature, but I haven't seen too much done on it in tropical cyclone work. And so looking at this relationship in observations would be tough, just because in the past, you're looking at tropical cyclones generally occur over the tropical oceans. In the past, observations of SST and precipitation over the tropical oceans have been kind of sparse and infrequent. It's getting better, due to satellites, the longer satellite record we have. But then also relatively short duration. So then it's also tough to estimate this climate change response when you only have like 20 years or so. But I think for tropical cyclones, the major interest probably is in how precipitation in these storms will react to climate warming. But the kind of question is, can we use this apparent scaling, so this present day variability, to estimate the climate scaling? And for my work, I was trying to see, can we use the climate scaling from these idealized simulations to estimate the climate scaling in the real world? So the model simulations I used, the idealized simulations I used are the same as the ones I just presented on. So there's those RCE simulations, but I just refer to them as RCE simulations in this work. And then I use more realistic simulations. So again, CAM5, kind of like AMIP style simulations. One is using observed SST for 1980 to 2012. And then I have this future simulation forced with simulated SSTs from long-term RCP 8.5 simulations for 2070 to 2100. And so the horizontal grid spacing of these simulations is also 28 kilometers, so same as the idealized. And these simulations have been used to study tropical cyclones in a couple of papers before, so I'm not like the first to look at the tropical cyclones in these simulations. And then observations, I'm using the observational period I'm using is 2001 to 2020, so it's slightly different than the time period used for the model runs. I'm using the IB tracks data set for TC tracks and intensities. For precipitation, I'm using the eMERGE satellite product. I convert it from half-hourly time steps to 6-hourly to match the model time steps, or the model output time step. And it's at, so the eMERGE is at a 0.1 degree spatial resolution, horizontal spatial resolution initially, but I regrid it onto a common grid with the models for the TC precipitation analysis. And then the SSTs from observations I get from the NOAA Optimum Interpolation database, which has daily temporal resolution and about 1/4 degree spatial resolution. And so for this comparison between the simulations and the observations, I'm only looking at TCs between 5 and 20 degrees latitude in both hemispheres, because I wanted to try to focus on the area where the idealized simulations may be the most comparable to the real world. So between 5 and 20 degrees, generally, it's mostly ocean. In the observations, I actually don't use any tropical cyclones that are right over land. If their center is over land, I get rid of them. But I just wanted to, focus on the area where the idealized simulations may be most comparable to the realistic simulations and the observations. So when you're comparing the SSTs under the TCs in these different data sets, so the blue is observations, the kind of historical AMIP run is the purple, the future AMIP run is the pink, and the RCEMIP, so those idealized simulations, are the black. And so first off, we see that looking at the blue and the purple, the observations in the AMIP historical SSTs beneath these TCs match up pretty well. There is a different, so this is just a pure count, 6-hourly time step count. The difference in the counts is mostly accounted for by just the different time periods looked at between the observations and the AMIP historical. And then, so most TCs in the present climate occur over SSTs between 299 and 303 Kelvin. So that's good. The historical is matching up with observations. It's forced by observations as well, so we would expect that. And then when you look at the future AMIP simulation, the distribution is kind of shifted towards warmer SSTs by about 3.3 Kelvin or so. And then we see the RCEMIP simulations occur at all SSTs, because that's just how they're designed. They're idealized. And so next I looked at, these are radially average profiles of TC precipitation rates in these same data sets. And these profiles are split up by the SST that's under the TC at the time. And so, I matched up the colors. So when you're looking at one color across the data sets, it's the same SST. And so there's a lot of things to look at here, but one thing I noticed is that at least in these radial averages, the AMIP historical actually has higher inner core precipitation rates than the observations. So that was kind of interesting. Across all of these data sets, as the SST increases, the TC precipitation rates tend to increase. But what is a little different is where the precipitation rates do increase. So we see in observations, there seems to be this kind of more uniform increase across the whole radial profile. Whereas in the models, there's more of an increase kind of concentrated in the inner core, which could probably related to the resolution of the simulations. They don't simulate outer rain bands very well, so I think that's probably maybe related to that. But yeah, overall they compare pretty well. The radial response is a bit different though, when you're looking at the response to the SST. So next I tried to dig down into this relationship between the SSTs and the TC precipitation. So this is just showing, again, 99th percentile TC precipitation rates on the y-axis, and then SST on the y-axis, with the colors representing, again, the different data sets. And so what you're looking at, so in the the background, those like light gray lines, is an increase of 7% per Kelvin, so approximately the Clausius-Clapeyron rate. So you can kind of use that as like a reference for these other lines. And so when you're trying to figure out the apparent scaling, so that present day variability of SST and precipitation, that's just shown by the like slope of those colored lines. And so we see that generally they're pretty close to the Clausius-Clapeyron relationship. The exact kind of estimated slopes are shown in the legend in the bottom right. Yeah, generally around the Clausius-Clapeyron. I also show the 95 percentile confidence intervals, which are larger for the observation since there's less samples. But generally, they do agree pretty well. They're all in the same ballpark. They're all within the 95% confidence intervals. Generally close to the Clausius-Clapeyron rate, a little bit above for the models. And then to try to estimate the climate scaling, so this climate scale relationship, it's basically kind of the shift between the purple line and the pink line. So that shift in that line between the historical simulation and the future simulation. And so if we were to just see a Clausius-Clapeyron shift of about 7% per Kelvin, then the pink line, that pink solid line, would match up exactly with that dotted purple line. So that dotted purple line is just a shift of the solid purple line by about 7% per Kelvin. And remember, there's about a 3 Kelvin increase between the future and the historical. And so what this shows, at least how I estimated it here, is that the climate scaling between the AMIP historical and AMIP future runs is a little bit below the Clausius-Clapeyron, about 5% per Kelvin. And if I instead try to estimate that climate scaling using the RC-EMIP simulations, which how I did that is I just took the cooler half of that black line and used that as like the historical, and then took the warmer half of that black line and said that was the future, and I kind of calculated that same shift. And that was estimated about 7.7% per Kelvin, so a bit larger than the estimate from the AMIP simulations. So results for part 3, and again, I'm still working on this a bit. This paper is currently under revision, so if people have comments or on this, I'd be happy to hear them. But it appears that the apparent scaling of tropical cyclone precipitation is a bit higher than the climate scaling. So we should be careful in studies about using the apparent scaling to estimate the response of TC precipitation and climate change, because again, they might not really be the same thing. This is consistent with previous studies that look at non-TC, just like general extreme precipitation. Why is the climate scaling less? This is a great question. I'm trying to look into this a little bit. One thought is that it could be due to the increase in the atmospheric moisture deficit in the tropics in the future. So maybe there's just not less moisture available, but the relative humidity change. Relative humidity is shown to be very important for tropical cyclone precipitation. So some effects of the moisture deficit. This has been looked at a little bit in future climate simulations relating to TCs. It kind of goes into some of the Genesis potential indices and various things that try to estimate future changes in tropical cyclones. So that's one thought. I think it could also be, again, related to the resolution of the models I'm using. It was only 28 kilometers. Maybe it's something, with the parameterization of precipitation that is maybe getting something wrong. A little unclear, but the good thing is the apparent scaling in the models is pretty close to observations, and again, the observations do have a bit of uncertainty because of the sample size. But generally, I think the models do see a very similar apparent scaling of TC precipitation with SST. Looking at the climate scaling from that figure in the previous slide, it seems that the RC-EMIP simulations may overestimate the climate scaling, at least what it is in these AMIP simulations in CAM5, which again, this is also just one model I'm looking at, so this could be very model dependent as well. And then also, one thing I did not show here is that the scaling rate estimates can depend on precipitation metric and other analysis choices, which again, I didn't really show here, but there is some, no crazy changes, but there is some variability when you depending on what metric you're looking at. And so I just thought, I phrased this title of this talk as a question: how and why does tropical cyclone precipitation respond to climate change? So I was like, okay, maybe I'll try to answer this question, even though obviously we don't have all the answers. But I think, about 7% per degree Celsius increase is a good first guess. It's likely to be a bit above that, I would say, in general. But again, it depends a little bit on precipitation metric. And then also, again, when you're looking at specific locations and specific storms, it's going to depend on the TC landfall frequencies, how fast they're moving, their intensities at landfall, maybe changes in outer size again. So I think what I've found is kind of a general change, but it's not unreasonable to see changes like way above this as well, I think, for individual storms. And then why is it changing? It seems like it's mostly due to thermodynamic factors, so just this increase in moisture. It seems that the changes in intensity are kind of secondary, although it's not that they don't matter. But I think this is important because in the future, TC precipitation is going to increase with little reliance on how much the TC intensity increases. So it's still kind of uncertain how much we expect TC intensities to increase in the future. But as far as TC precipitation risk, I don't think that matters too much. So now I'm just going to talk a little bit about what I'm doing or what I'm starting to work on in my postdoc. And so this is I'm trying to get at if we can examine changes in TC precipitation with warming at a bit of a smaller scale. So recent studies using observations, using, I believe, the TRIM satellite observations, have found this decreasing trend over time in inner core TC precipitation, so like within the eye wall, and an increasing trend in outer rain band precipitation. So I think this is super interesting. More than one study has found it, although they are using, I think, usually the same precipitation product. But I think if there is an increasing trend in outer rain band precipitation, I think that's really important for like TC hazard flooding purposes, because that can mean a greater area at risk when TCs do make landfall. So what I wanted to try to look at is do really high resolution models see these spatially varying trends within TCs in their rainfall? And then if so, why would inner core precipitation be decreasing? That kind of is a little counterintuitive, at least to me. So what I propose to do is to run these idealized WRF simulations using a modified, idealized TC test case. So this is a TC in a limited domain over just ocean, and kind of do something similar to what I did with the camp simulations, but run these simulations with different domain constant SSTs at very high resolution, so grid spacing of about 1.67 kilometers. In this vortex following inner nest, so very high resolution over the whole storm. I also am adding in this uniform zonal background flow, so the storm kind of moves around, because I know previous studies have found if you just have a storm sitting in the same place in these simulations, they get very, there's not a lot of outer rain band convection, and they're kind of not very realistic looking. And so I want to take these simulations at different SSTs. An example of what this looks like in a test simulation, it's the reflectivity at 2 kilometers horizontally in a vertical cross section, and kind of look at how 3D precipitation structures within TCs change due to SST warming. And so again, this is what I'm kind of really working on now. I'm still running these simulations and working out how to run them. But I want to compare precipitation in the inner core versus the outer rain bands in these different simulations. If there are differences, try to figure out why. Is changes in moisture convergence? Is there more outer rain band activity as the SST increases? I also want to use a tool that is used in Kristen's group a lot, where we can break down precipitation into like convective and stratiform, see if maybe there's more or less convective stratiform precipitation as SST increases as well. And so then after I finished hopefully these limited domain idealized simulations, I then want to try to, one, see if I see similar changes with warming, probably in like pseudo-global warming experiments like the 4-kilometer regional WRF-CONUS thermoglobal warming experiments. Kind of try to look at TCs in those, even though it kind of is a limited domain, but see if I see similar changes as what I saw in the idealized simulations. And then another thing I'd like to do, maybe if I have time, is kind of look at some of these precipitation structures in observations, maybe from GPM, or I think there's a CloudSat database that might have some of this already, or maybe even radar data, and see if, kind of compare if these idealized simulations are comparing well to observations. And so I think looking forward kind of even more in my research, and I think anyone who's at the atmospheric model working group meeting, we kind of saw a discussion of this, and those are perfect kind of openings for this talk, is that climate models are kind of approaching the ability to resolve the mesoscale and finer scales. And so there's kind of this convergence of global models. Maybe we'll see these high resolution kind of WRF simulation like TCs like in the global models. So I think that's really exciting for climate weather kind of interface research. I think it kind of can provide a lot of opportunities, but I don't think I think I'm preaching to the choir here when I say that finer grid spacing doesn't necessarily mean better storms. There needs to be kind of looking at process-based understanding of precipitating storms, not just tropical cyclones, obviously all storms, comparing to observations, kind of work on better parameterizations in these models, understanding why they're biases, how we can simulate them better, and then hopefully, ideally, get better projections of future hazards from these storms, because that's what at least motivates my my research in this area, is that hopefully we can help people in the future by better predictions of these hazards. And so that's all I had today. I'd be happy to take questions now or after the talk, or I put my email up here if anyone has thoughts afterwards. But thank you so much for listening.
Okay, thank you. So we're going to open it up to questions. So if you have a question in the room, please raise your hand. Myself or Julio will come around and hand you a microphone. And then again, if you are online and you'd like to ask a question, just go to slido.com and look for the CGD seminar page, and I can see if you've posted those. All right, so it looks like we have quite a few questions. So I'll go over here first and then come back to you, David.
Thank you for the talk. I just had a question, I guess, about the planned work you have with WRF. It's been a really long time since I've run WRF a lot, but I used to, and I remember one of the challenges was they have so many different physics packages. Mm-hmm. So how are you, maybe things have changed, but is there like a suggested physics package? Because I know microphysics and boundary layer, there were like a whole plethora and you had to do all these tests. And I'm curious how, how you'll decide what to use for your simulations.
Yeah, so again, WRF was also totally new to me when I kind of went into this. So, I mean, what I did was I went to Michael Bell at CSU, and I was like, hey, I'm running these WRF simulations. I know you kind of have experience in this. Like, what do you suggest as the parameterization packages? And so he kind of gave some suggestions. I don't remember the exact ones I'm using, to be honest. There are so many. But I think there kind of is a bit of a convergence on what ones are good for TCs, at least in these idealized simulations, as far as representing the boundary layer and like the fluxes and stuff. But another thing I'm thinking about doing is doing a bit of testing of different, probably maybe microphysics packages, and seeing how different the results would be.
In the AMWG meeting, Bill Skamrock showed TCs that lack strong spiral band structure and look like donuts. I'm wondering if you're seeing that in your results.
Yeah, so I mean, the one thing I did show was like these composites of, well, these are the idealized ones. But again, these are composites over like thousands or tens of thousands. Looking at TCs, I don't think I have any individual storms plotted in this presentation, but they don't look like annular like this when you're not compositing. They do sometimes have, some like semblance of outer rain bands, but they're generally like definitely less intense than the rain band precipitation you see in observations, and probably also larger. So I think that, that's definitely a downside of these simulations, but I'm kind of hoping with my future work of kind of getting at that problem a little bit more, but I think that does add some uncertainty into the results.
Thanks for a really nice talk. I am curious about how you decided on extreme precipitation metrics. You touched on that a little bit, and more specifically in the scaling line plots where you're showing 99th percentile. Is that defined independently for each of the simulation periods, the 99th percentile, or is it sort of one baseline that you're comparing?
Yeah, so it's defined by data set. So basically, and I kind of took this methodology, again, I kind of ripped it from extreme precipitation literature, kind of to see what they did. And so basically what you do is I bin the tropical cyclones into the SSTs by like 1 degree. And then I take all of the precipitation rates that are in all tropical cyclones in that SST bin, sorry. And then it's the 99th percentile like of that. And so it's like very extreme precipitation. So it does, the 99th percentile is defined by the different data sets. As far as choosing the metrics, so 99th percentile I kind of chose, again, based on this extreme precipitation literature. It's also kind of used in other studies like to try to compare. I also looked at, for this study at least, I looked at the mean precipitation within 1 degree, so to try to get to inner core precipitation only. And so the results are general. I didn't show them because they're generally consistent with what you see with the 99th percentile for the most part. But I think it's tough to compare all these studies because a lot of people do use different metrics. And I'm not suggesting that we just like focus in on one metric. I don't think that's a good say, like this one's the best. I think maybe it's good to look at multiple just to see how they compare, or maybe it's good if we try to find a metric that's best to input into like TC risk modeling or something like that. Maybe that would be a good avenue to go by. But.
Yeah, I had a question about the RCE setup.
Mm-hmm.
You said you introduced rotation.
Mm-hmm.
So I'm wondering what the zonal mean climate looks like. There must be a interesting general circulation in there with mid-latitude jets and things.
Yeah, so basically, I did look a bit at the general circulation, but there actually is a paper. It was probably, I think, the first group to look at these type of rotating RCE simulations on a globe. And so they dug pretty deep into the general circulation, so I didn't really do that too much. But basically there is kind of a Hadley cell, a bit that and I did this a long time ago, so I'm kind of reaching back here. But and there's really not much vertical wind shear though, so it is very weak. There is some in like the tropics. And then I think maybe kind of, TCs really like dominate in the poles. So I'm not sure like how much that, but there is some structure of like a Hadley cell at least, but I think beyond that, it was kind of very, very weak of like what else.
I was wondering about the shear.
Yeah, the shear is pretty, there is shear in the tropics a little bit, but it's definitely much weaker than like the average in a lot of like the North Atlantic basin or something. It would be less, yeah.
Hi, that was a great talk. I had 2 quick questions. One is for your scaling, and I think it was in your second part. If you look at different intensities of storms,
Mm-hmm.
if you bin them by different intensities, do you get a different scaling?
Yeah, I feel like I did do that at some point, and I think it was like there was less. It was a little closer to the Clausius-Clapeyron, and that's been done in other studies as well. And kind of when you try to take away the TC intensity effect, you do see something that's like closer to the Clausius-Clapeyron scale. I believe I did that, and I think that's what I found, but I can't remember exactly.
And then my second question is more of like the impact side. So like you're looking in your second and third part, you look a lot at like ocean
Mhm.
precipitation, and I was wondering how that translates to anything that's going to happen on land.
Yeah. Yeah, so yeah, I did in this third part, I did just look again at TCs that were only over the ocean, just because so I could try to compare them to the idealized simulations. Um, I think, I mean, I think as the TCs move over land, like they are bringing the moisture like from the ocean. So I imagine like it's not going to be any less of a scaling increase. I know there is, and there's also a big impact again of like how slowly the storm is moving, like how the precipitation rates kind of like change as it's moving over land. But I know that there is a group that kind of looked at the scaling, the climate scaling just over the Atlantic Ocean and then like just over the land. And they actually found like a much greater scaling over the land, which I don't think they really know the reasoning yet why, but it could potentially be even greater. But.
Okay, I think, yeah. And then we'll take-
Thanks, it's a great talk. So I guess I have a question and a comment. My question is, for example, in this figure, when you bend the precipitation to SST, how do you define the SST under TCs? Is it average over in an area?
Yeah, great. I didn't mention that. So yeah, so I'd say SST average over about a 5-degree box around the TC center. And I have done some sensitivity testing of that, and it doesn't really seem to matter. I'm also using daily SSTs in the observations, so I think that you know, that's a kind of a longish time scale, maybe, or like I don't know how much the SSTs are going to change on that daily time scale. So I think I even like did a correlation analysis of like the SST that's like just under the TC center, and then the 5-degree by 5-degree box, and there was like very high correlation. Like so, I don't think it would impact this scaling very much.
Great. I guess another comment is that I think is the slide before this one, you're showing the radial. Oh yeah, this one. I'm wondering if the difference between observation and the AMIBs are due to the ocean feedbacks, because in the observations you're actually taking into account the SST feedback to your TCs, but in the AMIB is just ultimate supply of heat fluxes.
Yeah.
So.
No, that totally could be it. It could also just be that and I'm not by any means like a satellite expert, but I know that maybe the observations, like the inner core precipitation rates, are underestimates, and maybe even the models are still underestimating, because I know it is hard to like see into the TC core and like really sense the precipitation rates that are really happening. So there is also observational uncertainty as well here.
Hi, so I'm not a climate person, I'm a weather person that studies hurricanes, and so maybe this question is trivial. So I'm wondering, by comparing the AMIP historical and AMIP future, why is there no overlap between the, let's say, 301 Kelvin radial rainfall profile? It's the same model, right? And
it's the same model. Yep.
And they have the same SST, and yet there's a difference. Why is that?
That is a great question. Definitely not trivial. So when you compare the overlap here, like the 301, they're actually, it's like similar, but I think even the AMIP future is like, a little bit less. So one thing I was thinking is it could be related to sample size a little bit, because like in the AMIP historical, like a 301 Kelvin storm or 302 is like a very like high, that's a high intensity for like the future or historical climate. Whereas for the AMIP future, that's kind of like a lower end SST. So I think there's kind of the TCs that are forming over those SSTs. There's less of them in the AMIP future, so the sample size is lower. And those tend to be like the weaker storms, I think, is one thought. And then I thought about this a little bit, and there was another. One other thought I had was also there is supposed to be an increase, or projected to be an increase in atmospheric stability in the future. And so maybe I was thinking there's some impact of stability here, or the moisture deficit change I was thinking of as well. Yeah, so those are my kind of two ideas, but I haven't dug into that too much. Yeah, that was a good question though.
Okay, are there any remaining questions? If not, I think we're actually at the end of the hour, or within 1 minute. So let's go ahead and thank our speaker again. And just as a quick reminder, if you are participating in one of the working group meetings, lunch is on your own, but we will reconvene at 1 p.m. For all the various working groups in the main seminar room. So thank you.
And don't forget to fill out, if you want to go to dinner tonight, there's the Google form on the meeting website.
And I think it's also in Elizabeth's email from this morning.
Okay.
So you can also go straight to your email for that.